In our everyday life, we use electric current almost at all times. While we're charging a phone, while you're using an iPad, while turning the light on, or running a machine, everything requires a current, electric current. But what is electric current? Where does it come from? So the electric current, in fact, comes from the charges. But there is a subtle difference here. If you have a charge and the charge is at rest, for example, when you rub two objects together, there are charges, but those charges are not in motion. If the charges are not in motion, then there is no electric current. For current to happen, the charges must be in motion. Okay, so the same charge, if it is a charge and the charges are in motion, it produces electric current. Okay, so here we have, let's say, an area, and this is sort of an imaginary area, and the charges, let's say electrons, or it could be any ions, the positive ions or negative ions, as far as it is charged, or even an object which does have charges. Okay, so this is an area, and the charges, again, as I mentioned, the charges, it could be due to electrons, it could be due to any positive ions. Okay, both positive, negatives, or if you have taken the semiconductor classes, then it could be even due to the holes. So if the charges are moving, then it produces an electric current, and it is defined how many charges, the number of charges divided by the number of time, or how many charges are crossing in a given amount of time, is the electric current. And this is the average, because the charges might not be crossing a given area exactly the same every time. It might be fluctuating with the time, and that's the reason we define the average charge. Okay, so if this number of charge and delta q amount of charge crosses this area in a delta t amount of time, then the average current is given by this equation. Okay, so, and I remember, this is a crossing, that means the charges are in motion. So the delta q is the total amount of charge. So how do we find out the charges? So there's another formula here, I'm just mentioned here, that delta q, if you know the number of charge carriers, let's say for example the electrons, or again the positive ions, and you know the charge of each carrier, then delta q is given by this equation. Or simply I can write this way: the delta q is equal to n, the n is the number of charge carriers, and the charge of each charge carrier, and q is the amount of charge, or the charge of each carrier. Okay, so this is the delta q. And the unit, now let's look at the unit here. You already have, and you already know what is the unit of charge. The unit of charge is coulomb, and the unit of time is second, and this coulomb per second is called ampere. So you might have heard about 1 amp, 2 amps, 5 amps, 10 amps. So what is in fact? In fact, this is the coulomb per second. So far we talked about the average current, and now let's talk about the instantaneous current. So the charge crossing an area here might not be constant, it might be fluctuating with the time. At 1 second, let's say 1,000 charges are crossing, but in the next 1 second, let's say 2,000 or 5,000 charges are crossing. So it is not constant, it is fluctuating with time. Then we defined the instantaneous current, And the instantaneous current is defined as dq over dt, or or mathematically we just say as the time tends to zero, then this equation is given by dq over dt. Or what does this mean? This means if a charge crossing an area is a dependent on time, or it's a mathematical function of time, and if you take the time derivative of charge, then what you get is the instantaneous current. So in general, the currents are measured in ampere, but sometimes sometimes currents are also measured in microampere, milliampere, or even a nanoampere. 1 microampere is 10 to the negative 6, milliampere is 10 to the negative 3, and nanoampere is 10 to the negative 9 ampere. Okay, so here again, just coming back here, what are the requirements? What do you need in order to make charge in motion? So this picture tells you the story. Okay, so what are the requirements? So let me write down here the requirements. The requirements for current. So the first thing you need is a potential difference. So this is called a potential difference. When I say potential difference, that means you have to have an electric field. This means electric field is required. And how do we get the electric field? We can provide this electric field by using a battery. A battery simply creates an electric field on a conductor. Okay, and the second requirement for current is the path, and this path could be, let's say, due to a wire, or even could be on a liquid. So there are different paths for this one, or even something human body is may provide a path. So these are the requirements, the two requirements: the potential difference, which a battery can provide, or a path. So here, this is a metal or a wire, and the wire has an ocean of electrons. And the moment we apply a battery, it creates a potential difference. Now let's try to understand a little bit here. So this is a positive terminal. So this is a positive terminal, and this is a negative terminal, right? And in metal, there are ocean of electrons. When I say electrons, that means these are the electrons here, which has the negative charge. What is do? That means the electrons will be attracted towards the positive charge here. The electrons will start moving in this direction. Okay, so all the electrons will now have a path, and this wire just provides a path here. This battery creates a potential difference. Okay, the difference, and the wire paths the channel, the path, and as a result, the electrons starts moving in this way. But you might be wondering why I have put an arrow here. What's the purpose of this arrow? So the purpose of this arrow is, or this arrow is indicating the path of the current. So traditionally or conventionally, the current path is opposite to the path of the electrons. So this is the direction of the electron, or this is the direction of the current. But in fact, if you look microscopically, then all the electrons might be moving in the opposite direction. So just for convention, the scientists, the people have used the direction of the current from positive terminal to the negative terminal. So this is the positive and this is the negative. And the current direction is always from positive to negative. So this is the current direction okay, which is from positive to negative. But in fact, the motion of the electrons are in fact happening in the opposite way, from negative to positive terminal. All right. So we talked about the requirements for the current. So now let's talk about again the direction. Coming back to the direction again. So if you have a positive charges, then the current direction and the charge direction is always towards the right in the same direction. But if you have, or in most cases, the charges are due to the electrons. So the current might be flowing. Let's say if this is the charge carriers, the electrons are moving in this direction. So this is the direction of the electrons. Then the current must be in the opposite direction. Okay, so this is just a sign convention. So just to remember here one more time, the current is always chosen from positive terminal to the negative terminal. But if it is a metal and if the charge carriers are electrons, then the electrons or the negative charge carriers always flow from negative terminal to positive terminal. And you see this is a positive terminal, so it might attract the electrons. So this is just a sign convention. It has been used for a long time. So this is it from this topic here. Again, if you have any questions, let me know. Okay, so far we just talked about average electric current and the instantaneous current, and in the next video I'll be talking about the drift velocity. Again, do not forget to like, share and subscribe the channel. Thank you very much.